Hey guys, today's screencast is going to explore reasons for the seasons. Why do we have seasons? Corresponding to this video, you have several questions to answer, so please have those questions out in front of you. If you need, feel free to pause or rewind the video, and let's get right into it. So, why do we have this sort of predictable change in seasons? Why do we go from spring to summer to fall and winter and back again? What is the cause for these cyclical changes on planet Earth? Well, it turns out there's a lot of misconceptions as to why we have the seasons. Many argue that it is the distance from the Earth to Sun that changes and therefore causes the seasons. That is actually not correct. We do remember, hopefully, that the Earth revolves around the Sun. That orbit is not a perfect circle, it's elliptical, right? It has a fairly low eccentricity, and so therefore it's slightly out of round. That means our sun actually is not at the center of our orbit, rather, it's at one of the focal points. This ultimately means that the Earth, as it orbits around the sun, is sometimes close to the sun or closer, and sometimes it's farther from the sun. We call these two different positions the perihelion, the point when the Earth is closest to the sun, and the aphelion, the point when the Earth is farthest from the sun. If you look at the dates when these two positions happen, though, you quickly start to understand that, oh, well, that doesn't make sense. If it was distance that is causing the seasons, why is it that we are closest to the sun during our coldest months? Our perihelion position is in January, and it's actually warmest in the northern hemisphere in July, and that's actually when we're farthest from the sun. So, with that information, we can quickly rule out distance as the cause for the seasons. Rather, what is the cause? There are two major reasons for the seasons. The first is the fact that the Earth is tilted. It's tilted by 23 and a half degrees with respect to the orbital plane as it revolves around the sun. So notice it's slightly off kilter, right? You see the North Pole, it's actually tilted by 23 and a half degrees. This tilt means that as the Earth orbits the sun, different latitudes receive different intensities of sunlight or strength of sunlight. There's going to be some latitudes that we're going to get to know very well as we study the seasons. Notice that the Tropic of Cancer is 23 and a half degrees north. The equator is at 0 degrees. And then south of the equator is what we call the Tropic of Capricorn. Each of these latitudes and all of the latitudes on planet Earth receive different intensities of sunlight as the Earth orbits the sun because of that tilt. So that tilt causes certain latitudes to get higher angle of sunlight. And a higher angle of sunlight means more absorption of that energy and a warmer temperature. Now, this isn't the reason alone because the Earth has to actually move in order for different portions of the Earth to receive different intensities of sunlight. In other words, the second reason is Earth's revolution. And Earth's revolution, we know, is counterclockwise as it orbits the sun. This is what helps us make an easy prediction as to what seasons will follow. If we see a position of spring, well, we know what comes next based on this counterclockwise revolution must be summer, followed by fall, followed by winter. So let's see both of these things in motion here. Let's actually play this out. Here's a pretty cool animation. Notice that the Earth is already rotating, right? It's spinning around on its axis once every 24 hours. And it's also going to revolve around the sun. Clearly, the scale is a little off here, but nevertheless, it's going to show both motions. So watch what happens as the Earth orbits into the summer season for the Northern Hemisphere. Notice which hemisphere is tilted towards the sun. Notice that tilt of the Earth is by 23.5 degrees and that the Northern Hemisphere is tilted towards the sun. Well, what does that mean? It means the Northern Hemisphere is going to get stronger sunlight, more intense sunlight when we compare it to the Southern Hemisphere. If I show you the Earth profile, here is the position of the Earth during the first day of summer. June 21st is what we call the summer solstice. Notice the direct rays, or the rays striking the Earth at a perpendicular angle, are happening right at the Tropic of Cancer. This is in the Northern Hemisphere. Therefore, it is this position that represents the first day of summer. In addition to the changing intensities of sunlight, take a look at the duration of sunlight, or the length of day. Notice the North Pole on the first day of summer has 24 hours of daylight. Since the Northern Hemisphere is tilted towards the sun, the North Pole is 100% consumed in sunlight. It's rotating in and out of sunlight. Look to the South Pole on this date. This is June 21st, so it's summer in the Northern Hemisphere, but it's winter in the Southern Hemisphere. Everything's flipped. Notice that the South Pole is rotating in and out of darkness. It's 100% consumed by darkness, 24 hours of darkness. So let's continue. That's the first day of summer. As we continue to revolve around the sun, following summer must come fall. We call this the autumnal equinox, and this happens every September 21st or 22nd, thereabouts. Notice now neither the northern nor the southern hemisphere is tilted towards the sun. Rather, the direct rays of the sunlight are right at the equator. You'll also notice there's an equal distribution of sunlight all over the world. That's why we actually call it the equinox. Equinox literally translates to equal day, equal night. So everywhere on planet Earth, there are 12-hour days and 12-hour nights, with the direct sunlight overhead at the equator at solar noon. After fall comes winter, of course. Notice the axis of rotation is not wobbling back and forth, it's remaining fixed and parallel. So in this position, 6 months after summer is the first day of winter. We call this the winter solstice that starts on December 21st. Notice where the direct sunlight is now. Since the southern hemisphere is tilted towards the sun, the direct sunlight is overhead the Tropic of Capricorn. Makes sense, right? We in the northern hemisphere will be experiencing winter, so it's a good idea to put your cap on. Now, those people living in the southern hemisphere are enjoying summer. The direct rays are at the Tropic of Capricorn. Look at the length of daylight now. The South Pole is 24 hours of daylight. It doesn't rotate into darkness at all. The North Pole is 24 hours of darkness. We can continue. After winter comes spring, of course. The spring, like the fall, is another equinox. So notice neither the northern or the southern hemisphere is tilted towards the sun. Rather, the direct rays are right at the equator. Again, everywhere on planet Earth is experiencing 12-hour days and 12-hour nights. Let's go ahead and take a look at some other interesting animations of this. Here's a good one. This shows planet Earth with the lines of latitude that we should get to know. Notice that we have the North Pole, followed by the Arctic Circle, about 66.5 degrees north. Here's the Tropic of Cancer, 23.5 degrees north. The equator, the Tropic of Capricorn at 23.5 degrees south. Antarctica, or the Antarctic Circle, and the South Pole. Now, take a look. The date right now is March 21st. That's the spring equinox. This is the first day of spring. Neither the northern or the southern hemisphere is tilted towards the sun. Rather, the direct rays, that's this line right here, are striking the equator. So the equator gets direct rays 2 times a year during spring and fall. The Earth has an equal distribution of sunlight and darkness all throughout its latitude. So everywhere on planet Earth, since it's the equinox, has 12-hour days, 12-hour nights. If you were standing at the equator at noon, since there's direct rays, the sun would be directly overhead. All right, let's hit play and see what happens. Now we're approaching the first day of summer. I'm going to stop it on the summer solstice, which is usually around June 21st. Now, the sun's rays are actually directly striking. Look at these most direct rays. The farthest north it gets is at the Tropic of Cancer. That's because the North Pole, or the northern hemisphere, is tilted towards the sun. So if you were at the Tropic of Cancer on June 21st at noon, the sun would be directly overhead. Notice if the Earth were to continue to rotate, the North Pole would never rotate into darkness. They would have 24 hours of daylight. Where we live, we do rotate into darkness, but these are our longest days. We have 15-hour days and 9-hour nights. Notice the southern hemisphere is mostly consumed by darkness at the South Pole, and this would have 24 hours of darkness. So after the summer solstice, we call it the solstice because the solstice means sun stop. The sun stops moving further north. It's like a bookend after this date, and it will start to go back to the south as the Earth revolves around the sun. So here we go. We're going to approach our next equinox, which is the autumnal one, which is right around September 23rd or 22nd. I just passed it by accident, but notice here the direct rays again are at the equator, and we have equal day, equal night. Neither the northern or the southern hemisphere is tilted towards the sun. Let's move into winter. The direct rays are now moving to the south in the southern hemisphere. They will stop moving south on the winter solstice, which is December 21st. And notice those direct rays in the winter solstice are striking the Tropic of Capricorn. They don't go any more south than that. So our direct rays really only fluctuate where the sun's overhead at noon between the Tropic of Cancer and the Tropic of Capricorn. With those direct rays in the southern hemisphere during December, now the northern hemisphere moves into their winter. The North Pole is going to be consumed by darkness, while the South Pole will be consumed by daylight. It's also kind of interesting to look at daylight in terms of how it changes throughout the year across the world. This is an interesting animation because it shows a map of the world, but it looks a little distorted because we know the Earth is a sphere, but this is sort of a two-dimensional image, a map. So it does look a little funny, but notice how you get some interesting changes in length of daylight at the North and South Pole depending on what season it is. For example, if we stop the animation here, this is July 20th. This is summertime, southern time in the northern hemisphere. In other words, look at the North Pole. Since the northern hemisphere is tilted towards the sun, the North Pole will have 24 hours of daylight. So we were just looking at the yearly variation. If I were to click on the daily variation here and start it, you could see as the Earth rotates, at the North Pole and at those northern latitudes, they will never see darkness during these summer months because the northern tilt of Earth's axis of rotation. The farther south that you go, the length of daylight decreases. And then if you go all the way to the South Pole, of course, you'll see it's totally dark, 24 hours of darkness. So again, this is summer in the Northern Hemisphere. So let's switch it up. Let's go to winter. And then I'll click the daily motion. And I'll hit start animation. And now this is December, getting close to December, getting close to the winter time. The date's November 26th. But as we approach winter here, we can see the southern hemisphere is tilted towards the sun, where it's experiencing just about 24 hours of daylight. So it's not rotating in and out of darkness. Rather, because of its tilt, it's 100% daylight. What you'll notice though is that the equator doesn't change much at all. It's always about 12 hours days and 12-hour nights. So there's very little change in the length of daylight at the equator. All right, guys, so we're going to stop there for today, and we'll talk about this in our next Zoom lesson. Thanks, guys.